Hello students, in this video we'll understand the connection between holomorphic and harmonic functions using the Wirtinger differential operators. Let's recall a real valued function f, which maps omega into R, where here omega is a subset of the complex plane, is harmonic if Laplacian of f is equal to 0, where we know what the Laplacian is. It's fxx plus fyy. Good. Now, let's recall also, and recall that that's what a harmonic function is harmonic, right? And the Wirtinger operators are df dz is 1/2 partial f partial x minus I partial f partial y, like that. And then df dz bar is going to be 1/2 and then d by f x plus I partial f partial y, right? We know a function's holomorphic if the z bar derivative is equal to 0, right? So the z bar derivative equals 0 implies the function's holomorphic, right? The z derivative being 0 implies that you're anti-holomorphic, right? So this being equal to 0 is anti-holomorphic, and this over here means that you're holomorphic. Good. Now, the beautiful thing is I can tie these together and use these as a way to factor the Laplacian. We've seen this in our Calc 3 class, right? In Calc 3, we talked about how we can factor these operators, right? So let's do it. So of course, now let's consider 4 partial squared f partial z bar partial z, right? What's this going to be? Well, it's going to be the z bar derivative of this thing over here. So it's going to be what? Of course, I'm going to take this 1/2 over here and this 1/2 over here, and that 4 will cancel both those out. Okay, so the 1/2 and the 1/2 and the 4 cancel out. Good. Now, what we really have over here is we really have the z bar derivative. So I have to do an x derivative plus a y derivative. That's the z bar of what? Of this thing over here, of partial f partial x minus I partial f partial y, right? And so what are we going to have? We're going to have two x derivatives over here. So we're going to have an x derivative. That's the second x derivative. Then we're going to have a what? Then we're going to have a negative I partial squared f partial x partial y. Then we're going to have a plus I partial squared f partial y partial x, so those are going to cancel. And then finally, negative I gives me a positive 1, so positive partial squared f partial y squared, and that's just the Laplacian of f. Great. What does this tell me? This tells me something very nice. It tells me the following. It tells me, okay, well, you're harmonic, so in other words, f harmonic, if and only if what? If and only if the z bar derivative of partial f partial z is equal to 0. If and only if partial f partial z is holomorphic. Great. Cool. Now, what can we say? We can say, since holomorphic functions have local primitives, at least locally have primitives, right? So partial f partial z has a local primitive phi. Okay. And so what does that tell us? That tells us that f of z is this function phi. That's what it means to be a primitive, plus a function phi of z, where its derivative with respect to z is equal to 0, where partial phi partial z is equal to 0. Okay, excellent. Then what I'm going to do is I'm going to consider the complex conjugate of this function little phi, right? Let's let psi of z be what? Phi of z complex conjugate, right? Okay. Well, then what can we say about phi, right? Then phi of z d phi dz bar is equal to d phi bar dz bar. But what is the bar of the bar, right? The bar of the bar is just itself, right? So this is just d phi dz complex conjugate, and we know that's equal to 0. Oh, cool. What does that tell you about little psi? Therefore, little psi is holomorphic. And so what have we done? we've done the following. Now we have f, this harmonic function f of z is what? Is going to be phi capital of z, that's a holomorphic function, plus little phi of z, but little phi of z is equal to psi of z. So that's psi of z complex conjugate, right? Complex conjugate. So it's the sum, so f is the sum of holomorphic in psi is holomorphic, so that's anti-holomorphic and anti-holomorphic. Beautiful. So I got a decomposition to the sum of a holomorphic and anti-holomorphic function. That's great. What in particular does that tell me? That tells me that I can write down a series expansion for this f, right? So in particular, near any point, f of z is going to be what? F of z is going to be the sum, n goes from 0 to infinity, of some numbers over here, a n, z minus a to the n, plus some other numbers over here, b n bar, z minus a n bar, right? In particular, this gives me a quick proof that in the plane at least, that every holomorphic function is also analytic, right? So this implies that f is analytic in omega. And that, of course, allows me to conclude that it satisfies the identity principle as well, right? So f satisfies the identity principle. And therefore, zeros can't accumulate. Okay, so we got a lot of mileage out of this very simple result, right? The mileage we get states that these Wirtinger operators tell us that there's a particular factorization of the Laplacian, right? So the harmonic functions can be broken up into two parts, the holomorphic part and the anti-holomorphic part, right? It's the sum of those two things. I can write down Taylor expansions for each part of those things and just simply complex conjugate everything. This is a continuous operation. Therefore, if it has a Taylor series expansion, I can write down what the identity principle is. There can't be, if two holomorphic functions agree on a set with an accumulation point, those holomorphic functions have to be the same. The same for harmonic functions. If you have two harmonic functions in a domain, and they agree on a set which has an accumulation point, they have to be the same function. Beautiful, right? What's one sort of classic application of this? The classic application of this says that application, that is used all the time, if f is holomorphic and zero free, that implies that the log of modulus f of z is harmonic. Okay, why is that the case? Well, the log of the modulus of f of z is the real part, right? It's the real part of what? It's the real part of the log of f of z, which exists because it's zero free. In particular, what this is saying over here is, what is this decomposition saying over here? If you want to find out since f is real valued, what is it? It's going to be the real part of f plus phi, right? So f in particular, according to this thing, is just the real part of phi plus psi, by symmetry, right? And so in other words, f is the real part of a holomorphic function. So it's the real part of a holomorphic function. Okay? Now, this is true locally, right? And I can take the idea of local, because it has locally as a primitive, right? Because in a domain, I can find a ball, a small disk in that domain by openness, right? It's an open set. Now, what I can say is I can say that I can remove the local assumption, the fact that it's locally the real part of a holomorphic function, by a global statement, provided that the region is simply connected, which we'll discuss in further videos. Okay, we'll discuss simply connected in further videos, but suffice to say that the reason I'm using the real part is the imaginary part of this thing is not defined in the neighborhood of the origin. So I cannot define globally what the imaginary part is because what's happening? The argument's changing, right? The arguments is what's making the logarithm mess up a little bit. So the real part is nice and is nice when the real part, when f does not vanish. That's a beautiful harmonic function, okay? And that harmonic function comes up all the time. We're going to really key in on this particular harmonic function because it relates to the Green's function and helps us solve the Poisson equation, right? So we're going to really focus in on this. It's going to come up in a lot of different applications. So we'll see that in further videos. Thank you very much.